In this video, we are going to see about the application of root locus diagram and Nyquist stability criterion. Application of root locus diagram. The stability of the system can be calculated. The effect of variation of parameters so that the limits of these parameters can be determined for stable operation. The method is particularly suitable in the design stage of the system when there is some latitude in the choice of the system parameter. The root locus plot technique can be applied to determine the dynamic response of the system. This method associates itself with the transient response of the system and is particularly useful in the investigation of stability characteristics of the system. It can also be used to determine the stability boundaries of the system. Selection of suitable parameters may be made using the root locus analysis. It is a well-established fact that the condition of root of the characteristic equation governs the transient behavior and hence the stability of the system. In the root locus plot technique, which is essentially a graphical procedure, the locus of the roots on the S-plane is affordable by the variation of the suitable parameter. The root locus plot are drawn in the complex plane as the roots may be real or complex. In this technique, also the open loop transfer function may be used to simplify the procedure. The plots drawn and the information obtained from these plots pertain to a closed loop system. The plots clearly illustrate the effects of variation of parameters on system stability and the nature of the response. The branch of a root locus shows all the possible values of one root when a parameter is varied. All these separate branches of the root locus plot give the effect of the variation of parameters. The root locus plot technique is essentially a time domain technique. Frequency response data can be obtained from the root locus plot. Using this technique, the open loop poles and zeros can be modified to satisfy the requirements to be met by closed loop poles and zeros. It may be noted here that a slight change in the pole 0 configuration may cause significant changes in the root locus configuration. The Nyquist stability criterion determines the stability of a closed loop system from its open loop frequency response and open loop poles. If we take a complex number s equal to x plus jy on the S-plane and substitute it into a function f of s, another complex number results. This process is called mapping, the collection of points called a contour. Contour A can be mapped through f of s into contour B by substituting each point of contour A into a function f of s and plotting the resulting complex numbers. The contour B maps in a counterclockwise direction if f of s has just poles that are encircled by contour. Also, you should verify that if the poles of zeros of f of s is enclosed by contour A, the mapping encircles the origin. The Nyquist stability test is obtained by applying the Cauchy principle of argument to the complex function. Cauchy's principle of argument: let f of s be an analytic function in a closed loop region of the complex plane given in figure except at a finite number of points. It is also assumed that f of s is analytic at every point on the contour. Then, as travels are around the contour in the plane in the clockwise direction, the function f of s encircles the origin in the plane in the same direction n times. The above result can be written as argument of f of s equal to 2 pi n, which justifies the terminology used the principle of argument. The Nyquist plot is a polar plot of the function d of s, which is equal to 1 plus g of s h of s when s travels around the contour is shown in the figure. The Nyquist stability criterion states that the number of unstable closed loop poles is equal to the number of unstable open loop poles plus the number of encirclements of the origin of the Nyquist plot of the complex function d of s. This can be easily justified by applying Cauchy's principle of argument to the function d of s with the S-plane contour given. Note that Z and P represents the number of zeros and poles respectively of D of S is the unstable part of the complex plane. At the same time, the zeros of D of S are the closed loop system poles and the poles of D of S are the open loop system poles. The above criterion can be slightly simplified if instead the plotting function d of s equal to 1 plus g of h of s, we plot only the function g of s h of s and count encirclement of the Nyquist plot g of s h of s around the point -1 to j0. Nyquist plots are the continuation of polar plots for finding the stability of the closed loop control system by varying omega from -infinity to infinity. The Nyquist criterion works on the principle of argument. It states that if there is p poles and z zeros are enclosed by the s plane closed path, then the corresponding g of s h of s plane must encircle the origin p minus z times. So we can write the number of encirclements n as n equal to p minus z. Let us now apply the principle of argument to the entire right half of the S-plane by selecting it as a closed path. This selected path is called Nyquist contour. The poles of the characteristic equation are same as that of the poles of the open loop transfer function, and the zeros of the characteristic equation are same as that the poles of the closed loop transfer function. The Nyquist stability criterion states that the number of encirclements about the circular critical point 1 plus j0 must be equal to the poles of the characteristic equation, which is nothing but the point of the open loop transfer function in the right half of the S-plane. This shift in the origin 1 plus j omega naught gives the characteristic equation plane. Rules for drawing Nyquist plot. First one is locate the poles and zeros of open loop transfer function. Second, draw the polar plot by varying omega from 0 to infinity. Draw the mirror image of the above polar plot for values omega ranging from -infinity to 0. The number of infinite radius half circles will be equal to the number of poles or zeros at the origin. This infinite radius half circle will start at the point where the mirror image of the polar plot ends, and this infinite radius half circle will end at the point where the polar plot starts. After drawing the Nyquist plot, we can find the stability of the closed loop control system using the Nyquist stability criterion. If the critical point lies outside the encirclements, then the open loop control system is absolutely stable. From the Nyquist plots, we can identify whether the control system is stably or marginally stable or unstable. Gain crossover frequency and frost gain margin and phase margin can be calculated using Nyquist plots. Phase crossover frequency, the frequency at which Nyquist plots intersects the negative real axis, is known as phase crossover frequency. Thank you.